Welcome to 1007 ICT, 1807 ICT, 7611 ICT, Computer Systems and Networks. This is Lecture 8, Computer Networks. Last time we covered the history of operating systems, the idea of starting up the machine through a process called bootstrapping, the process that's running at all times called the kernel, the ideas of managing all the different parts of the environment, so the process management, scheduling the CPU, dispatching jobs, managing the memory, and then virtualization. They were all topics we covered in the operating systems section. So in this section, we're going to start talking about networking. So from here on in, it's about the networking communication part of the course. We'll be talking about computer communication, the OSI model, TCP/IP, data transmission, network topologies, and network categories. So a broad range of things. We're going to learn about them and gain an understanding of these things. So we're not necessarily going to do much processing with this stuff at this point. Again, you'll get some practice with this in the workshops, but it's more informational at this point. Just what is the environment that we're working in when we're talking about networking? So the basic idea is if we want to transfer some data from one computer to another computer, we have to somehow connect those two computers together. There are many different ways to do that, and you probably have used some of those when you're using a phone or when you're using a cable, plugged into a PC, plugged into a wall somewhere. But the idea is that we need to connect their input and output subsystems together. So in this diagram down the bottom, you've seen that one before. There's computer A and computer B. On the left, there's a processor with the control and the data path. We spent a little bit of time looking at that. In the middle is the memory. Again, we spent a little bit of time looking at how memory works. And on the right, we have these input and output devices. We've talked a little bit about those. We talked about interrupts, for example, and some of the ways that we communicate with the different devices. At this point, we're going to talk about how do we connect one of these input-output systems to the other one. And you'll notice with the arrows there, the input of one is going to the output of another one. Yep, so they're kind of crossed over. Right, so one of them is talking, the other one is listening, and the reverse happens as well. So to communicate, we need a physical connection between computers to transmit over. Now it says physical, that does not necessarily mean a cable. It just means something or some way to send information from one physical machine to the other physical machine. It could be wireless, could be any kind of communication medium. We need an agreed data representation for exchanging the information. That should make sense. If I'm speaking in English and you can only understand French, for example, right, that's going to make it very difficult for us to communicate. We can still communicate, but we need to translate something in between. Does that make sense? Yeah, or we need to agree on the language that we're going to use to communicate. And not only do we need to agree on the language, but we also need to agree on the set of rules or procedures to coordinate that exchange. For example, in this lecture environment, I'm talking, okay, and you're listening. We have agreed before this point that's this kind of environment. This is how this particular environment operates. Do the workshops operate the same way? No, they have a slightly different set of rules, and depending on what context you're in, you'll have different rules for how you communicate. If you're talking to your friend on the phone, you will have a different set of rules. Yep. So you need to know what those rules are, though, otherwise everyone tries to talk at once, or no one talks, or any of the variation on those two extremes. So a computer network is a collection of computers that use one or more network protocols to exchange data with each other over a network medium. Network is the collection of computers. Network protocols are these set of rules for us to communicate, and the medium is the way we are communicating. So is it over the air, is it through a cable, that kind of thing. So a protocol is a set of rules, procedures, or technical specifications that is used to exchange data successfully. You will see the word protocol a lot in networking. It's just a set of rules for how you're going to do something. A protocol defines a number of things. What extra information needs to be sent to transfer the data? Maybe I need to send some information about, if I send you this information, if you want to check that it's correct, maybe I have to send you some extra information. We saw that in the error detection and correction section of the course. The meaning of each bit in a data transmission. Well, we talked about little and big endian before, right? So if I'm speaking big endian, then you need to interpret those values as big endian values. If you interpret them as little endian values, we're going to have some difficulty communication. And how to send the data and when and how fast to send it. So if I'm speaking very fast, that may be too fast for you to keep up with. Yep. So I try to regulate how fast I speak so that it's still possible for you to understand what I'm saying, and it's still possible for me to get everything done within the hour that we have. Okay, so there's some kind of adjustment that's made there. And networks or networking environments do a similar kind of thing. And you may have had an experience where you have a really slow device and a really fast one. They must communicate in some way so that that's possible for that communication to be successful. The data communication process. So data communication involves the exchange of information, binary data, and signals. And it depends on which level you're looking at, which type of information you're working with. So information or the messages is between people. You know, if I send a message to my friend, I'm going to send some text or a picture or something, and they're going to get some text or a picture, and we're going to use that information to make some meaning from it. But the computer doesn't use those pictures, it doesn't use the text, it uses, at some level, a lower level, the binary data. Right, so ones and zeros. So all the information, the text, for example, that I've got is just stored as ones and zeros, and that's the application to the application layer. So the application, the program, doesn't understand the meaning of the text, it just understands, here are the symbols that you want me to send. Okay? And again, that's an abstraction, or that's not the actual physical stuff that gets sent. If you're talking to the communication subsystem, the actual thing that's connected to the wire, for example, it's not going to send ones and zeros. If it's connected to a physical cable, it will send electrical signals. Up and down, or high and low. Right? So there's a translation that happens there. And that is a computer, to network communication. So we had so far user to user, that's the text that we see, application to application or computer to computer, which was the binary values, and then the computer talking to the network and the network talking to the computer. Those are the different levels. So transferring of messages involves source encoding, conversion of the user information to binary data, because I'm a user, I use text, for example, it has to be converted to binary somehow. Transfer of data from the application to the communication subsystem. So my program wants to send something across the network. There has to be a process for doing that. And it has to be organized and packaged in some way so that that's actually feasible. For example, one of the things that might need to happen is that I'm going to send a really big message. Now maybe I can't send it all at one go, so I have to chop it up into separate parts. Can you see that might be one of the steps? Yep, so maybe that happens somewhere along this process. At the bottom is the transmission or sending of the data over a given medium. So the computer, in some sense, or the thing that's talking to the network, has to understand how to send information on that particular network type, that cable or that wireless environment, whatever it's using. So we have the OSI reference model. So last century, the International Standards Organization developed something called the Open Systems Interconnect Model. Those are fantastic acronyms, ISO, OSI. So OSI is the reference model, ISO is the standards organization. And that model describes a total of 7 different layers of services that a network protocol needs to address. So if you have a network protocol, you need to do, according to this model, 7 different things. There are 7 steps that you go through. Each layer builds on the services of the layer underneath it to provide some more advanced functionality. So starting from the bottom, we start with the physical layer. Then we go to something called the data link layer, the network layer, the transport layer, the session layer, the presentation layer, and the application layer. Now each of those layers, we haven't talked about what they do yet, but each of them has a specific job, and they build on each other. So you can do something very, very complex with 7 different layers, but each layer is not as complex as all 7 of them together. So you simplify things. Okay, we'll talk about these layers in detail, by the way, so we don't need to know exactly what each one of them does now, but you need to know that there are a number of these layers, and each of them has a specific job, and that job is necessary to get the communication to work the way we want it to work. So here is a summary of those layers. This is a really good slide. This slide, slide 9, if you're studying for an exam, for example, this is a nice single slide that has everything on it. At least at a high level, you're going to have to do a little bit of work in terms of reading about these different layers later on, but these are a simple English description of what these layers are doing. So if you're looking, let's start at the top. At the top layer, I've got the application layer. This is the program. This is the one that I'm using to send my message. It defines what message I'm going to send. So I've typed some text in, that's the message. There has to be an application or something that does that for me, captures that information. The presentation layer defines the format of the message. Now that could be something as simple as Well, it's a really big file, I want to compress it. Or I don't want other people to read it, I want to encrypt it. Right? I change how it looks. So there's a layer that deals with that kind of stuff. The session layer defines when messages can be sent. Do you think I can send messages whenever I want? I can try, but probably there are some restrictions on that. Does that also make sense? Yep. So maybe I have to coordinate in some way, synchronize in some way. The transport layer, it's the layer that's responsible for sending the whole message across the whole network, so from start to finish. Now, if you look at the line below that, the network layer sends not the whole message, but a data packet across the network. So at this point, somewhere in between here, we had a whole message, and now it's been chopped up into data packets, smaller chunks. And the data packets ideally are roughly the right size, or the right type for the network that we're on. Yep. Okay. Below that, the data link layer sends a data packet, so that hasn't changed, but it doesn't send it across the whole network, it sends it across to the connected device, so my neighbor. And my neighbor is then responsible for getting it to their neighbor, and their neighbor, and their neighbor, until eventually it gets to the endpoint. Can you see how we're changing the scope, or the things that these layers are concerned with? And at the bottom layer, the physical layer, well, it doesn't work on packets. It says, I've got a packet. What are the bits in this packet? And I'm going to send these bits one by one as some kind of signal right across this network, and I send it to my neighbor. So starting at the bottom, you'll see that the physical layer is sending individual bits to the neighbor. The data link layer doesn't really care about the bits, it cares about packets, so chunks of bits, and it sends it a packet to a neighbor. The next layer above that says, well, I don't really care about individual packets, I care about the whole I care about individual packets, but I don't care about my neighbor, I care about the endpoint. Then the one above that says, well, I don't care about packets, I care about the whole message, and I care about the endpoint. And then above that, we talk about, well, I've got a whole message, when can I send it? The one above that says, well, what should it look like? And the one above that says, well, what is the actual message? So you can go either way with this. So this is a really nice slide, I think, in terms of just getting a conceptual overview of what's actually going on with all the different layers, without the detail, by the way. There's not much detail here. So there are two different models that we tend to talk about. We talk about the OSI model, which is the reference model, and the TCP/IP model, which is the model that we actually use in principle, in practice. So OSI is strictly a model with no implementation. It's not one we use on a day-to-day basis. Some people have probably implemented it, but that's not the point. It's a reference model. It says these are the things that you should be doing if you were going to build an environment for networking. So OSI is virtually unused by itself. It's a copyrighted in principle standard, so it's the reference. And in practice, when you're using your networking environment, you're probably using TCP/IP. Have you heard that term before? Yeah, or at least IP or TCP. So you're using the TCP/IP protocol suite. It has an associated implementation stack, which is basically someone has written code to make it work, right, on different environments. And it's in widespread use. It's a de facto or in practice free standard, one of the reasons why people use it. It's also the basis of the internet. And basically TCP/IP came before OSI, which is why we started using it. And then they said, okay, look, if we were doing this again, maybe we would do it slightly differently, right? And you can see here there's a distinction between the two models. On the left is OSI, has our 7 layers we talked about, and they sort of map to the TCP/IP layers on the right. So application, presentation, and session on the left map to one big application layer level on the right. Transport network and internet seem to be sort of similar. Maybe not the same, but similar. Data link is split up into 2, logical link control and medium access control, and the physical layer obviously is mapped across as well. So there are some similarities, but they do things slightly differently. And the key thing to remember for us is that we have a standard, it's TCP/IP, does the same things, maybe it does them in slightly different orders or slightly different ways. If we're communicating through these layers, here's an example of encapsulation. So when you see a word like encapsulation, we don't use it that much. You can try and look at what it's made up out of. So what kind of word do you see in the middle of encapsulation? I see capsule, right? So when you think of a capsule, it's, you know, something that has some stuff inside it, Yeah, so if you go to the chemist and you buy a capsule of some drug or whatever, right? It's got some powder inside it. Usually you eat it, right? So encapsulation in this sense basically means wrapping something up, all right, and moving it through a process in this case for the layers. So I'll go through to the diagram, I think. It makes it a little bit easier to talk about. So as a user, so this is me here. I'm working on a web page. Now, a web page that I see is text and diagrams, and it's just inside a browser, right? Is there code behind this web page? Yeah, there's some code, some HTML, CSS, whatever the different environment is that they're using, but I just see it as a web page. At the application layer, what I'm looking at is HTTP, which is the protocol for the web, right, the hypertext. Okay, so if I'm going to send a message across a network that's supposed to be a web page, it needs to be in HTTP. Now, what that means is on the other end, when they get this, they need to know that it's HTTP, which means I'm basically thinking of this as an envelope. I'm stuffing my web page inside the envelope, and on the front, I'm writing HTTP and any other information that's necessary for the person on the other end to work out what to do with this information. Right? Presumably, they're going to show it on a web browser, right? So they need to know that what the standard is for doing that. The transport layer says, look, I don't care about HTTP. I have an envelope with HTTP stuff and some stuff in it. I don't care about any of that. What I care about is this TCP protocol, right, which is the one that I'm using to communicate. So on the other end, when the transport layer on the far end gets this message, what do they get? They get TCP stuff. And then they can look inside and they go, oh, it's HTTP, and then they can go, oh, here's the actual data inside that HTTP stuff. Can you see we're kind of like wrapping stuff up and then wrapping it up and wrapping it up, and every time we just put something new on the front. It's like a new envelope with a new address. So the network layer says, okay, look, I'm responsible for getting this thing across somewhere, right? Now to do that, I use this IP environment, or the Internet Protocol. Okay, this stuff here, well, it's made up of TCP, HTTP, and then the web page. I don't see any of that at this layer. I just see my IP header. And it might be something as simple as what's my address, what's their address. Yep, just the IP addresses that we're working with, and so on. At the data link layer, well, we're now connected to a physical network. For example, Ethernet. If we're working with Ethernet, then every Ethernet frame has an Ethernet header saying, look, I'm Ethernet. There's all the stuff that you had, the yellow stuff there is all the packages that you had, right? The internal bits of data that you built up. And then at the end of this frame, it's the end of the Ethernet frame, so you have a frame check sequence for Ethernet which says, here's some information about the frame you just got. You can check if it's correct or if it got corrupted or something like that. Can you see we're just building bigger and bigger packets or frames or whatever we call them at different layers? You notice the names change as we go down because they're different layers. And at the end, we just turn that into a signal. What do you think happens on the other end? They get an Ethernet frame, so they take off the front and the back, and then they have all this stuff. They send it up to the network layer, who gets the IP address stuff and takes it off, and then they send it up to the transport layer, who takes off the TCP stuff, sends it up to the application layer, who says, oh, it's HTTP, okay, fine, and then you give it to your web browser. Is there a lot of work involved? Yes, it's actually very, very stressful in some sense on the environment that you're working with. You don't see any of this stuff, right? But there's a lot of processing that happens to make this work, and it works very, very fast. Okay, so that's just a very simple illustration of communicating through these layers. So now we move on to the physical layer. So the physical layer is responsible for ensuring that a stream of bits are transmitted between two nodes sharing a single link. Just want to point out at the top right of this page, you'll see the 7 layers, and one of the layers is highlighted, right? That's the layer we're on at the moment. So when you're going through the slides, you'll see the layer kind of indicated, because there's 7 of them. It's easy to get lost in terms of, you know, which one we're at. So the physical layer coordinates all the functions required to transmit a bit stream over a physical medium, right? So stream of bits. It defines a whole bunch of things, the physical characteristics of the interfaces and the media. So I'm connected to a physical network. I have to know how to talk to it. That means if I'm connected to a cable, I have to be able to send electrical signals through that cable. Representation of bits. How are the zeros and ones encoded? how do I turn them into, that electrical signal, for example? Or if it's on a fiber optic link, how do I turn it into light? Right? What's the algorithm or the process for that? The data rate. How many bits can I transmit per second? Depending on what I'm connected to, that will be different. If I'm connected to ADSL, for example, it's going to be different than if I'm connected to fiber. Right? The speed will be different. Synchronization of bits between the sender and the receiver. We're communicating. You will tell me sometimes, stop, I'm busy, or I didn't get the last thing you sent me, or whatever happened, right? So we have some way to process that. The line configuration. Are we talking single point, I'm just talking to you, or am I talking to a bunch of people on my network? Am I broadcasting, or am I just talking to a single place? The physical topology, the mesh, star, tree, ring, or bus. How is my network actually configured? Depending on the environment that I've got, maybe I've got a mesh, unusual, maybe I've just got a star type shape of my network. I'll draw some of these in a little bit. And transmission mode, simplex, half duplex, or full duplex. And this is basically saying, look, can we both talk at the same time or not? Or do we have to wait for each other, or can only one person talk? Does that make sense? So depending on how you've configured it, you'll need to make sure that that's processed in that particular way. Looking at the different ways to transmit stuff, well, you can transmit stuff in parallel or in serial. So in parallel on the left, inside the computer, typically it's done in parallel, and there's a line between every bit. So between two registers, you'll transmit the bits, all 8 of these bits, transmit in one time unit. Is that feasible outside the computer? Not really. So we have this serial transmission typically on the outside, where you send a bit at a time. You send them really fast, but basically you just send them one after another, and then you have to grab them one after another on the other end. Which one do you think is faster? Parallel or serial? Parallel looks to be faster, right? Everything else being the same? Yeah? Okay. The electrical interface is to transmit binary data over any communication link. You must convert those things into electrical signals. And the only criteria for us really is that the signal must be a 1 or a 0, because we're storing stuff in binary, so 1s or 0s, and we can use voltages or something like that to represent the differences between those values. The data rate, so how much data can be sent in a channel, is measured in terms of how many bits can be sent per second. This is the speed that you transmit stuff at. So the data rate is defined as bits per second, or BPS. There's variations on this, but for us it's BPS. And if you look at this diagram, in 1 second I can send 8 bits. I have an 8-bit per second network connection. Would you be happy with that network connection? 8 bits per second. No, very, very unhappy, right? What are we up to these days in terms of our, let's say, home internet speed? Megabits per second? Maybe someone who's lucky has got gigabit per second, right? So it really depends on what your environment is, but bits per second is very, very slow. So we would expect this to be much, much faster. And all you can see is if it's faster, the 1s and 0s are squashed together more closely, right? Okay. Latency, the transmission delays. So latency is the time required to transfer a message between the source and destination computers. It measures a bunch of different delays. Propagation delay, which is the time taken for the signal to travel from the source to the destination. Transmission delay, the time taken for the whole message to pass some point along the transmission path. Access delay, if you're accessing or you're using a network, you might have to wait for some resources to become available. So you have to wait for them to be accessible. So there's an access delay. And then the routing delay. If you're sending information through a network, it goes through these machines like routers and switches and so on, and they will delay the message just because they have to do some work to find out where it goes. Right? So there's all these different delays as you go through the network. And you can add them up and you can get some sense of the total delay, or the total time that's being wasted not actually sending this message but waiting for particular things to happen. Different network connections. So network devices can be connected to each other via cable, a wired sense, or over the air, a wireless sense. So how many devices are connected together defines the type of network configuration. There's 2 possibilities, point-to-point and multi-point. So we've got switched and broadcast there. We'll talk about that in more detail. But basically point-to-point is me to you, one-to-one, and multi-point is there are multiple places that I'm going to. The physical or logical layout of a network is called the network topology. So you may see this word topology so now and again. Topology is basically the skeleton of the network. So if you're looking at it from a really big height, you're looking down on it, you'll see the backbone of the network, right, between the different machines, so the cables. There are 5 possibilities that we'll talk about. So let's have a look at the different possibilities. So some of the, like, I'm just going to draw them, but some of them are pretty straightforward. So this is a star network, right? So there's a big node in the middle, and there are some nodes in or around the outside. So it's a star, it looks like a star. If you look down on it from the top, you'll see it looks like a star. This network has some advantages and some disadvantages. One of the advantages is that if I want to communicate from here to here, it's a very small number of steps, right? Here to here, small number of steps. So the number of steps between 2 nodes is the same, actually. It's actually very small. One of the problems is that if this node goes down in the middle, I don't have a network. So it's not very robust. It's not very stable in terms of if things go wrong. Does that make sense too? So there might be better types of networks. But this is a pretty cheap network. It doesn't have a lot of cabling, right? The machine in the middle needs to be fairly powerful in terms of getting all these connections. But you know, it's a fairly useful, quick, but not particularly robust environment. A ring network. Well, here's a ring. So this is nice in the sense that, you know, it's very cheap in, you know, terms of cabling, but it takes a bit of time for me to get from here to here, for example, right? So I've got to go through multiple steps, as opposed to the star, which is very quick. It sort of suffers from a similar problem as the star. If this one goes out, well, I still have a network. I've just got to go the long way. If I lose 2, so it's a bit more robust than the star network, but it's still not particularly great in terms of, you know, if things go bad. The bus network, well, we've got something that looks like this. So basically, there's a shared line or a pipe that they're using here. Okay, same sort of idea. It's like a ring network. It's very similar. If you just tied them together, you'd have a ring. Does that make sense? Okay, so this conceptually anyway. Some problems with the bus network is if you break the bus, then you disconnect the network. Now, actually, you might have 2 separate networks. They just can't communicate across that break. And obviously it takes longer time to go through here, right? The other issue with the bus network is typically a bus, multiple people can try and use the bus at the same time, so you might have some collisions and, you know, to have to deal with people trying to use it at the same time. The mesh is another simple kind of idea. Basically it's just a grid, and there we go. And it might even be like this. Right, so you might have these kind of things and so on. Does that make sense? So it might be fully connected. Now, if it's fully connected, basically, you know, you would have this kind of setup. So if you wanted to knock this network out of action, you would need to do a lot of damage to it because it's very robust in terms of there's so many links going everywhere that, you know, you have to knock out a lot to make it not connectable. Does that make it more expensive? Yeah, absolutely. It's much more cabling. It's much more difficult to cable as well. Each of these nodes needs to be more expensive, right? They need to have more capacity to handle all the links. So there's some downsides, but obviously if you're looking for a robust network, something like this would be better than, say, the star network. And the tree network, this is the last one. So the tree is actually, it's an upside down tree. So here's a tree. And you'll notice that the top there, this is the root, and these are the leaves down the bottom. So there's some nice properties of a tree. Depending on what kind of tree you have, you can have a very nice ratio in terms of how many things you have to go through to get to the endpoints. It's reasonably robust. If you knock this one out, you have 2 separate trees. You can't talk to the different parts, between the different parts, but this part of the tree is still perfectly fine. Right, so you know it's sort of robust in that sense, but you can be very efficient with a tree. So you see a tree structure used fairly frequently in lots of different environments. So that's just a visual representation of some of these types of networks, and you can see they have different properties. You might choose one over the other depending on what you're trying to achieve. So the links that we were talking about, well, they can be guided or unguided. So a guided medium has some kind of conductor, something, you know, copper or whatever, that restricts the path of the communication signals, and it's got some kind of coating around it, you know, to stop interference or whatever. And some of them are shielded to stop the interference, some of them are not, depending on the particular application. We talked about data errors, so probably you would prefer a shielded cable in case there are some interference or something that, you know, affects the cables that you've got. An unguided medium, in contrast, does not restrict the path of the signal so that it's transmitted in either all directions or in the general direction of the intended recipient. So microwave radar, radio waves, satellite, infrared, they're all unguided medium. Although the microwave radar is a particularly fine point, it still spreads out, right? So it's not it's not in a cable, but it's particularly good for getting a fine point across a distance. But it's still not guided. Unguided media can use two kinds of antennas. Directional antennas, they emit a radio signal to one point, so it's point to point, and you need to align things. Omnidirectional antennas spread it out around, sort of a radius or circle, and they're better for multi-point connections. You can use them for point to point as well if you want. So I guess if you're at home, what kind of router do you have? Network access point. You probably have a omnidirectional one. Yeah, it's better for you in terms of the house because you might be anywhere in the house. If you know where you're going to be, you might have a directional one, right? It might be better. You might get a better signal strength. In terms of network configuration, so point to point, those connections provide a dedicated link between two devices. Each device can communicate only with those that are directly connected to it. So you look, there's a workstation with a link between it, connected to another workstation. They can communicate because they're directly connected. Anything that's not directly connected, they can't communicate to each other. So on the right, you'll see the same diagram, but now the phone network is in the middle. So they're still directly connected. There just happens to be a phone network in the middle, right? So they can communicate with each other. So they communicate with other computers not directly connected. They have to do via an intermediate relay. So basically, in the bottom, you'll see there's a workstation connected to the middle workstation, connected to the right workstation. So the one on the left is not directly connected to the one on the right. There is no way for them to directly communicate with each other. So if they want to communicate, the one on the left has to send a message to the workstation in the middle. I think I have a diagram for this. Yeah, so the one on the left, this guy, has to send a message to here. And this one says, oh, you want to talk to this guy? Okay, I'll send it along. So that's the standard internet type model when you're sending messages from your computer to another computer somewhere else in the world. Is this inherently secure or insecure? What do you think? It's insecure because your message goes through multiple points on the way to the destination. And at every point, the one in the middle can read your message unless you take steps that they can't read it. Does that also make sense? So you might have some secure versions of certain protocols that let you hide the information. Is that still safe? Well, they still get the message, so if they can decrypt it or find out what the message is, it's still not particularly safe. So just keep that in mind in terms of these communications. Just by the nature of how you're working, it's not necessarily secure. Okay, so microwave and satellite are point to point. So a microwave link has a very fine beam, very powerful, but it's not guided. It just basically goes from one point to another and it spreads out over time. So you have a limited amount of distance you can use it for. The satellite, you'll notice that there are some satellite sending to the satellite, and there's a receiver at the bottom. So the broadcast satellite is a special case of this, where if you want to send something to a satellite, you need to know where it is. You don't just send it everywhere. Right, you could do, but it would take a lot of power. So you find out where the satellite is, and you point directly at it, and then you send the signal there. It's like a satellite phone, that kind of idea. You have to point it at the right place. But on the other hand, the satellite, because it's so high up, it can just broadcast, and everyone can get that information. So it has two different approaches there. In terms of the network configuration, we have this idea of a switched network. So in many networks, rather than directly connecting computers together, you connect them to devices called network switches. They're also called multi-point routers sometimes, depending on the particular flavor of them. But let's just call them switches for our purposes. So a switch switches between things. You'll see in the diagram down the bottom there's circle things in the middle. Those are switches. So switches permit multiple dedicated point-to-point connections to be made between a number of computers in the network at once, even though they're not technically directly connected all the time, but it's fast enough that you won't notice the difference. And communication between any two nodes can involve passing through several switches. So again, just having a quick look at a diagram. This one at the top here wants to talk to this one. Now, at the moment, without these switches in the middle, there's no way to connect them. But if you go through the switches, then if you turn this switch this way, and this switch this way, and this switch this way, you can get to that particular machine. If you wanted to get to this machine, you could go through this one, you could turn this switch this way, this one, and this one. Can you see how if you change the configuration for the switches, you can get the different machines connected to each other, and you can do that very, very quickly and change the connections over time if you like. There are three different categories of networks that we talk about. We have the local area network, the metropolitan area network, and the wide area network. And those categories are distinguished by dimensions, so how big they are, and ownership. Typically different kinds of companies or businesses or governments own those. And then the physical architecture, what do they actually look like? So internetworks, it's the idea of having different types of networks connected. This is different from the internet. So the internet is the network that we use most of the time. We're now talking about an internet, which is just a bunch of different networks that are connected together somehow. And they're connected via some kind of internetworking devices, so routers and gateways and different kinds of boxes that allow communication to happen between the different kinds of networks. If they're different kinds of networks, do they speak the same language necessarily? What do you think? No, they won't necessarily. They might do, but they probably don't, because they're different kinds of networks. So something might need to translate between the different networks to make sure that the communication is successful. And you'll see here that there are, local area networks as routers between those R's in the boxes are routers, for example, and they're all different kinds of networks. But you can connect them together if you put those boxes in between. So local area network, it's mostly designed for computers to share resources like printers, and probably most people at home have some kind of local area network that they've configured right behind their router and firewall, whatever. Links up to hundreds of devices in a single building. Probably you don't have that many at home. And a local area network will generally use only a single type of transmission medium. Most common LAN topologies will be bus and star, and they're usually privately owned and operated. So example here, there's a single building one, so I'll use the university as example. If you go to a lab, it's a single room in a building, or maybe two rooms next to each other, and they're on the same local network. Right, maybe 60, 100 computers all together across a couple of labs, right, and they're all on the same specific part of the network. And in a different building, those computers would be on a different local area network. Now they are connected together in some way, which is like that picture I showed you just before, and they may be connected through a backbone network. So a backbone network is a larger central network that connects several local area networks together. Now you probably don't have one of these at home. Right? It's certainly possible, but it's unlikely. And they typically span up to several kilometers, and most common backbone topology is bus and star, and again, they're usually privately owned and operated. In terms of the university, well, this is a multiple building local area network, and each of those buildings might be one of the labs or a couple of those labs that we're talking about. Now, in between these buildings, so this is a particular lab. And it's one particular local area network. If I want to talk to the lab over here, it has to go through this backbone network. So there must be the backbone network, which is the one in the middle here. That's the one that connects the other networks. So I have here 1, 2, 3, 4 different local area networks. They're all connected by this middle backbone kind of network. Metropolitan area network extends over an entire city, so 5 to 50 kilometers, maybe 100 kilometers. Like it depends on the range, but basically it's one local geographical area. It's mainly used for interconnecting private local area networks, and that could be located in different areas to each other. So normally owned and operated by someone else, an independent or government service provider. So this could be comprised of these buildings, let's say here on, say, the Nathan campus for the university. We've got a bunch of different buildings. We've got some backbone networks connecting those things together, right? We also have other campuses. So we have the Gold Coast, South Bank, and so on, right? So if we want the entire university to be considered as one network, we would need to connect those, and that makes it a metropolitan area network, but it's quite a big area. We may not own all the infrastructure to be able to do that. For example, we might have to lease some lines between the Gold Coast and Brisbane. It's a big distance, right? It might be too expensive to buy that outright. And so typically someone else, a bigger provider, would own some of that infrastructure, right? That kind of makes sense. Wide area network extends over a large geographical area, an entire country, continent, or globe. Makes use of the public carrier transmission media like leased lines or the PSTN, ISDN, or the different kinds of telephone networks that are available. Wide area networks that are wholly operated by a single company might sometimes be referred to as an enterprise network. Okay, and that might be a very, very large company that might have something like that. Basic idea here, though, is this the scale, right? This is a much, much bigger scale. In summary for this section, we've looked at computer communication, the OSI model, TCP/IP very briefly, data transmission, and then network topologies and categories. Next, we look at the idea of packet transmission, and that's the end of this section.